Hi everyone. Earlier we were talking about the spectrum of stars, and remember that what is a spectrum? A spectrum is where you take the light from a star, a nebula, a galaxy, something, you shine that light through a prism, and the prism breaks the light up into the different wavelengths, the different colors, so that you can examine the different intensities at different wavelengths, or in this graph, different frequencies. But the two things are more or less saying the same thing. And we were talking before about how stars are hot and they're dense and they give off a continuous spectrum, which is true to a point, but actually it's not entirely. When you look at the spectra of stars, this is what they actually look like. Eventually, around 100 years ago or so, astronomers started making spectrographs that could see the spectra of stars in enough detail, with enough resolution, that you notice that you don't get a perfect blackbody spectrum. You're not getting all the colors of the rainbow like you do in this cartoon here. Actually, there's a little bit more structure here. There's a little more detail, that the spectra of stars have these dark lines in them. Each of these rows is a different star. Here's the spectral type, O, B, A, F, G, K, M. Here are the names of these specific stars. So HD 12993 is the sort of serial number for this specific star. But each of these spectra is from a different star. And all stars have these dark lines in them. What's going on there? Why don't stars give you a perfect blackbody spectrum? Well, in order to answer that, we need to look at the other two types of spectra that we haven't talked about before. So, I said before, there are three general types of spectra. The first is the continuous spectrum, as we said before. A continuous spectrum is what you get from a hot, dense object. If your object is not dense, if it is a low-density gas, then you end up getting the second and third, the second or third types of spectra. So that's what we're going to unpack here. In order to understand how low-density gases interact with light, we need to look at the structure of atoms. Because with a low-density gas, like the air you're breathing right now, there's a lot of empty space around or between the atoms and molecules. And since there's lots of empty space, photons can get in and interact with the atoms one-on-one. There's a one-on-one interaction between an atom and a photon. And that's why you end up getting a different type of spectrum. Right? With dense objects, the whole object is emitting or absorbing light. And so you get a continuous spectrum. But with a low-density gas, you end up getting the one-on-one interactions between atom and photon, and that produces a different type of spectrum. So to understand how atoms interact with light, let's look at the structure of an atom. Right? Here's the typical cartoon for an atom. You've got the nucleus made of protons and neutrons in here, and then out here you have the electrons orbiting around the nucleus, sort of the way that planets orbit the sun, right? This is the usual cartoon. And here we have a problem, because this is not the way electrons really look. This is not the way electrons really behave as they're orbiting around the nucleus of the atom. Electrons are way too small, they're moving way too fast. You can't pin down an electron and watch it orbit around an atom the way you can watch big slow-moving things like planets orbit around the sun. It's a lot more realistic to think about electrons as being this fuzzy, diffuse electron cloud, where all the electrons are buzzing around in here somewhere, but you don't know exactly where, and you don't know exactly where they're moving at any given instant. It's statistical, right? You can say, well, probably the electrons are in here. But you can't pin down exactly where. How do you solve that problem? That's a discussion for another day. The good news is, for our purposes here today, we don't need to know exactly where an electron is, and we don't need to know exactly what direction an electron is moving at any given instant, because what we care about is how much energy the electron has. And that is actually pretty easy to determine. So remember from way back when you learned this in junior high chemistry class or something, remember that in atoms, electrons only exist. They only exist in certain discrete energy states. Right? In this atom, the electron can either be at the lower energy level or the upper energy level. That's it. It can't exist anywhere in between. And so let's pretend, this is unrealistic, but we're going to pretend for a second. Let's pretend that this electron can only exist at these two energy levels in the atom, that there are no other energy levels. The natural inclination of all objects in the universe is to be at low energy. Everything in nature wants to settle down to the lowest possible energy state. And so, left to its own devices, this electron will settle into the lower energy level and just stay there. So how does an electron get into the upper energy level? Well, there's a couple of ways to do that. One of the ways is to heat up the gas. So let's say, instead of just a single atom, let's say we have an entire cloud of these gas atoms. All right? If I take this cloud and I heat it up, then the atoms start moving around faster. And when they move, they're going to start colliding with each other. And so an atom can come in because these atoms are moving really fast. An atom comes in, this atom collides with that atom, and in that collision, they exchange energy. This atom loses energy, and this atom gains energy. How does the atom gain energy? Specifically, it gains energy by the electron gaining energy, enough energy to jump up to the upper energy level. This electron, because this electron is in a higher energy level, it is now said to be excited. It's in an excited state. That's the term for it, when an electron is in an upper energy level. By heating up the gas, we're causing more collisions, faster collisions, and in those collisions, electrons can absorb energy and jump up to the upper energy level. And that electron will stay in an excited state for a few seconds. But eventually, like all things, it'll settle down. The electron will drop back down into the ground state, into the lower energy level. But how does it do that? How does the electron lose energy? The energy can't just disappear. Energy doesn't just disappear from the universe. So in order for this electron to drop down into the lower energy level, it has to lose energy. How is it going to lose that energy? By emitting a photon. That electron shoots out a photon, and that photon carries away the energy that the electron lost. This is how the electron loses energy, by emitting light. So what have I done? I've taken my cloud of gas atoms, I've heated up the cloud, those atoms collide with each other, the electrons get excited, the electrons de-excite. That's the term for it. The electrons de-excite, meaning they lose energy and drop down. And when those electrons drop down into the lower energy level, they emit photons, and now my cloud has started to glow with light. What kind of light is this? What is this light going to look like? Well, in order to understand the light that we see, we need to look at the energy levels themselves. So let's make this a little bit more realistic. Let's pretend that there are 3 energy levels in this atom. If the electron is in level 1, let's say it has 4 electron volts of energy. I'm just making up these numbers to make the math easy, to illustrate the point. But let's say in level 1, the electron has 4 electron volts of energy. In level 2, the electron has 8 electron volts of energy. In level 3, the electron has 14 electron volts of energy. So, if there are 3 possible energy levels, then this electron has 3 possible ways. Let's say this electron has 3 possible ways to lose energy. The electron can go from level 2 down to level 1. The electron can go from level 3 down to level 1. Or the electron can go from level 3 down to level 2. Right? If this electron is in an excited state, it's either up in level 2 or level 3, and it'll hang out there for a few seconds until it drops back down, loses energy, and it can lose energy one of these 3 ways. If the electron goes from level 2 down to level 1, it has lost 4 electron volts of energy. Where does that energy go? It gets emitted as light. And so when the electron goes from level 2 down to level 1, it's going to emit a photon that has 4 electron volts. The energy of that photon will have 4 electron volts. When an electron goes from level 3 down to level 2, the electron loses 6 electron volts of energy, and therefore the photon that gets emitted will have 6 eV. If the electron goes from level 3 directly down to level 1, that electron has lost 10 electron volts, and therefore the photon that gets emitted will have, sorry, did I say 4? That electron will have, the electron has lost 10 electron volts of energy, and therefore the photon that gets emitted will have 10 electron volts of energy. I think I may have misstated there a second ago. So, if I take these atoms, I heat up the gas, the atoms collide with each other, and the electrons jump up to level 2 or level 3, and then the electrons drop back down, and those electrons are going to emit light. But this light is not going to be like a continuous spectrum. This light is not going to give you all the colors of the rainbow. These atoms are only going to give off 3 specific colors. The color that corresponds to 4 eV, the color that corresponds to 6 eV, and the color that corresponds to 10 eV. 3 possible transitions mean this atom is capable of emitting 3 possible colors, and only 3 possible colors. Because when an electron loses energy, the photon that it emits has to have exactly as much energy as the electron lost. So this is why when you heat up a gas, that gas is going to start glowing, but that gas is only going to glow with specific wavelengths. This gas is only able to give off specific colors. Let's take helium atoms, for example. When you take a helium gas and you heat it up, that helium gas glows, but helium gas is only able to emit this one red wavelength, this one yellow wavelength, these 2 greens, and these 2 blues. Each of those colors corresponds to one specific way that the electron lost energy. And since the electron can only lose specific amounts of energy, this atom is able to give off only specific colors. This is our second kind of spectrum. This is what's called an emission spectrum. So when you take a hot gas, that hot gas gives off specific bright colored lines against a black background. And the important thing about this is that each element of the periodic table has different emission spectra. That every element in the periodic table, hydrogen, helium, lithium, beryllium, all of them, each element has different energy levels. And since they have different energy levels, essentially every atom has different numbers here. And since every element has different energy levels, when those atoms drop back down, when the electrons drop back down, each element gives off different energies of photons, different wavelengths of light. And so each element's emission spectrum is like a fingerprint. That pattern of colored lines uniquely identifies that element. And every atom of helium in the universe only gives off this pattern of lines. Every atom of sodium only gives off these lines. Every atom of neon only gives off these lines. So if you discover a brand new nebula, if you discover a hot nebula out there in the galaxy, you take the light from that nebula, you shine the light through a prism, and if you only see this pattern of lines, you go, oh, I know from lab experiments, I know that this pattern of lines is only given off by helium. So this nebula that I just discovered must be made of helium. This is how we know what things are made of. This is how we know what the chemical composition of objects is out there in the universe, is by looking at the lines in the spectrum that are unique to that element. So that's what you get. You get an emission spectrum when the gas is hot. What if the gas is cold? Well, if the gas is cold, then the collisions between the atoms are not very fast. No electrons are getting excited. Okay, not no. Very few electrons are getting excited in collisions from a cold gas. So in a cold gas, all those electrons are in the ground state. And since they're at their lowest energy levels, they can't lose any more energy, they can't give off light, which means they're very bad. Cold gases are very bad at giving you emission spectra, but those electrons are very good at absorbing light. So if there's this cold gas, and then if light comes shining in, then that photon can get absorbed by the electron. If this electron absorbs this photon, that electron gains the energy from the photon, and it'll jump up into the upper energy level. Notice, where did the photon go? It disappeared. The photon got completely absorbed by the electron gained that photon's energy, and the electron jumped up to the upper energy level. This is essentially the opposite process of what we had before. Right? Here we have a cold gas soaking up light, whereas with an emission spectrum, you have a hot gas giving off light. This is how cold gases interact with light, by absorbing it. But this photon can only get absorbed if this photon has exactly the right amount of energy to take the electron from the lower energy level to the upper energy level. If that photon does not have just the right amount of energy, it can't be absorbed. It passes right on through the cloud and comes out the other side. So this is what you get when you have a cold gas, right? Here are two spectra for hydrogen. If this hydrogen is hot, then that hydrogen gives off that one red wavelength, that one blue wavelength, these three violet wavelengths. If the hydrogen is cold, then all of the electrons are at level 1 or level 2, and the cold hydrogen is not very good at emitting light. But if you take a continuous spectrum, you take all the colors of the rainbow and shine it through the cold hydrogen, those cold hydrogen electrons will absorb this one red, this one blue, these three violets, because these are exactly the right wavelengths that take an electron from a lower level to an upper level. And therefore, these are the only wavelengths that those electrons can absorb. All of these other colors don't have just the right amount of energy, so they pass through the cloud for us to see. So those are the other two types of spectra, right? If you have a hot gas, it emits specific wavelengths. That's an emission spectrum. If you have a cold gas with a continuous spectrum shining through it, then you're going to see all of those colors from the continuous spectrum, except you're going to see all the colors from the continuous spectrum except for those specific wavelengths that got absorbed by the cold gas. This is how we can figure out what things are made of. This is how we figure out what things are like out there in the galaxy. If you're looking at some object out there in the universe, you take the light from that object, you shine it through a prism. If you see a continuous spectrum, then you know, whatever that object is out there in the galaxy, I'm seeing a continuous spectrum, so I must be looking at a hot, dense object, and then you can use the peak wavelength to figure out what the temperature of that object is. If your mystery object gives you bright lines against a black background, then you say, aha, that's an emission spectrum. So whatever my mystery object is, it must be a hot gas. And then the lines that you see in the spectrum can tell you what the gas is made of. But if you see all the colors of the rainbow except for those dark lines, then you know, aha, I must be looking at a continuous source shining through a cold cloud, and then the light reaches Earth. So you can do, with an absorption spectrum, you get the best of both worlds. You can see the continuous spectrum, so that you can take the peak wavelength to figure out the temperature, but you can also take the dark lines to say what elements absorb light at those wavelengths. Now I know what the composition is. This is what we see from out there in the galaxy. Right? When you have a hot cloud of gas, like an emission nebula, like the Ring Nebula here, an emission nebula will give you bright lines. And so you can look at those lines individually, and you see an emission line here, 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 etc. And you can scan across the whole spectrum and say, what elements do I know of that emit light at those wavelengths? And you can say, well, this one comes from oxygen, this one comes from neon, this one comes from hydrogen, this one comes from nitrogen, sulfur, and therefore, what is this nebula made of? It must be made of oxygen, neon, hydrogen, nitrogen, and sulfur. This is how we know what elements are in these clouds. To get back to that first question that we started with at the beginning of the talk, why do we see an absorption spectrum from stars? I thought stars were hot and dense. That's what we were saying before, right? It's true, right? The core of a star is hot and dense. The core of a star gives you a perfect blackbody spectrum, a perfect continuous spectrum. But the surface of a star, the outer envelope of a star, is made of cooler, lower density gas. And so, what does a cool, low density gas do with light? It absorbs it. So the core of the sun, let's say, the core of the sun is giving you a continuous spectrum. But as this light leaves the sun, that light has to pass through this cool, low density layer, and this cool, low density gas is going to absorb out those specific wavelengths, so that what we see leaving the sun and reaching the Earth is an absorption spectrum. Right? The solid, not solid, but the dense core of the star is giving you a continuous spectrum. The outer layers absorb some of that light, and so what we see here on Earth is all the colors of the rainbow, except for those specific lines, those specific wavelengths that got absorbed by the outer envelope of the star. Right? This is how we know what stars are made of. All right, we don't have to travel to all the stars in the galaxy to figure out what they're made of, because the spectrum is telling us. When you look at, now this is a very high resolution spectrum, right? We can see lots and lots of detail from the spectrum of the sun. But what you're seeing is, you're seeing all the colors of the rainbow, except for all of these dark lines that got absorbed by the surface of the sun as the light was passing through it. And so you can look at these dark lines and say, well, the darkest lines must come from the most abundant elements. And lo and behold, what are the darkest lines? What element is absorbing strongest? in the sun's spectrum? What element is the strongest absorber in the sun's spectrum? Hydrogen. Why is there so much hydrogen absorption in the sun's spectrum? Because the sun is mostly made of hydrogen. What's the second strongest absorber in the sun's spectrum? Helium. So the sun must be also made of a lot of helium. Right? All of these darkest lines, this one here, that one there, these ones, a bunch down here in the blue that are kind of hard to see, that one there definitely. All the darkest lines here are from hydrogen and helium, because the sun is mostly made of hydrogen and helium. All of these other lines, all the minor lines in the sun's spectrum, are from elements that are in minor abundances. Every star, to loop back to that very first diagram we were looking at here, right? Notice all stars have absorption lines right here, right here, right here, right there, right there. What are those lines? Those are hydrogen and helium absorption. Every star, it's not just the sun, every star is mostly made of hydrogen and helium. The difference is, what about the minor lines? What about all these little lines? Those can be different. In astronomy, we don't talk about the chemical elements the same way they do in a chemistry class. In astronomy, there are basically 3 elements in the periodic table. There's hydrogen, there's helium, and then there's all the other stuff. Because every other element in the periodic table, from lithium all the way down to uranium, every other element in the periodic table is in a minor abundance. Our universe, all the stars, all the nebula, our universe is overwhelmingly hydrogen, mostly hydrogen, with a lot of helium and a little bit of everything else. Oxygen, carbon, iron, calcium, silicon, gold, uranium, all of it. In astronomy, we have a little bit of jargon where we take all of these minor elements in the stars and we lump them all together and we call them metals. And I put metals there in quotation marks because this means something a little different than when you talk about metals in a chemistry class, right? When you take a chemistry class, metals are like gold and copper and iron, right? Solids. In astronomy, metals, in, dubious quotation marks, is just anything that isn't hydrogen or helium. Right? There are 3 elements in the periodic table of the universe as far as an astronomer is concerned. There's hydrogen, there's helium, and there's metals. And everything else we just lump all together and say, that little stuff. The stuff that there's not that much of. Some stars are more abundant with metals. Some stars are less abundant with metals. Every star is mostly hydrogen and helium. But stars can have a little bit less or a little bit more metals. And so we measure the relative abundance of metals in a star by measuring what we call metallicity. I promise I didn't just make up that term. Right? So the metallicity of a star is metallicity is a measure of how enriched that star is in heavy elements, in metals. Right? So let's say you look at a star and that star has a spectrum like this. Most of those lines, the strongest lines are going to be from hydrogen and helium, but all of these little lines, they're from metals. But there's only a few lines, right? There's not that many lines. So you could look at that star and say, well, there aren't that many dark lines, so that's a lower metallicity star. There isn't that much carbon, oxygen, iron, silicon, metals in that star. Whereas then you look at this star on the bottom, and this star has lots and lots of dark lines. Because this star is more enriched with more elements absorbing more light, causing more dark lines in the spectrum. So you could look at that star and say, oh, that's a higher metallicity star. Why do we do that? Why do we look at the different metallicities of stars? Well, for lots of reasons. One of those reasons, though, is because when you start looking for planets around those stars, when you start looking for planets around other stars out there in the galaxy, what are planets made of? Well, planets like Earth are made of heavy stuff, right? Earth is made of iron and nickel and silicon and oxygen, all of which are called metals, as far as an astronomer is concerned. So what's the Earth made of? The Earth is made of metals. Your body is mostly made of metals, right? Your body is made of carbon, oxygen, nitrogen, calcium, iron, right? Your body is mostly made of metals. So if we're looking around the galaxy trying to find Earth-like planets, if we're trying to find planets that might be habitable, if we're trying to find planets that might have life on them, rocky planets like Earth and living things like you and I are made of metals. So where should we look in the galaxy to find metals? Let's look around metal-rich stars. Right? We don't know where to look in the galaxy to find life yet. Beyond the Earth, that is. But if we're trying to find the best bet, if we're trying to say where should we be looking in the galaxy to find planets that might have rocky planets like Earth and might support life, let's look for stars that have a lot of metals. Because if there's a lot of metals in the star, there might be a lot of metals orbiting around the star in the form of planets. So high metallicity stars are a really good bet for where we are going to find Earth-like planets and possibly life-supporting planets out there in the galaxy. If you find a star that has very, very, very low metallicity, then you could look at that and go, well, that's an interesting star. It's very low metallicity, but the odds of it having life orbiting around it, very low. So that helps us winnow down the possibilities for where we should be investing our time and energy to find life out there in the universe. All of which we can get from looking at the spectra. Right? Spectra, looking at the spectra of stars doesn't just tell us the temperature. It can tell us the temperature, but it can also tell us composition, relative abundance, age. It can tell us the age, although that's a more complicated story for another day. But it can also tell us where we might finally find life out there. And that will help us when we're starting to find alien planets, like we're going to in a few days in class. All right. Thanks, everybody. Hope you have a good day.